Hey everybody, and welcome to McCardle Math Academy. In this video we're going to be talking about work, and we're going to be doing the chain problem. So let's look at this
example here where we have a 40-foot long chain that hangs off the side of a building. We're given the weight density of the chain, so let me circle the weight density here. And we want to figure out how much work is needed to pull the chain to the roof of the building. So let's look at the picture here and actually talk about why calculus is even needed. So think about yourself up here on the top of the building, and you're pulling up on this chain. So here you are up here. Initially, the chain's going to be pretty heavy because it's all suspended from the roof. But then as more and more chain accumulates on the roof, you're going to find that your job is a little bit easier. So the force that you need to apply to this chain is varying. And when you have a varying force, we have the need for calculus. Okay, so what we're going to end up doing is saying, okay, let's divide this chain into little chain links. So for example, here is my little link. It's going to have a length of dy, and it's going to be located at a height of y. Alright, before I started I should have set my reference, so my 0 point's going to be here, and all the way up at the top we'll have our 40-foot mark. Alright, so upwards is the positive direction. And now you have freedom to set that reference wherever you like, and the setup of the problem will change, but the result will be the same. So there's my chain link. What you want to do is you want to focus on that chain link and say, alright, how much work is needed to raise just that chain link from the original position, it starts at a position of y, all the way up to the top. We know what work is, so essentially we're trying to find the work for that slice. So what we're looking for here is the work for the slice, and we know the equation for work is force times the distance that the slice travels through, so force times distance. We have to look at each of these pieces separately. Force, there's only one force pulling down on the slice, which is gravity, so we're going to have an equal force in the other direction. So this is just going to be the weight of that slice. And then we're going to multiply this by the distance. And if you look at the distance here, this little red slice is going to have to move through this blue distance, which is given by 40 minus y. So it all depends on how high we started. If it started at a height of 10 feet, we're going to have to pull it 40 minus 10 or 30 feet. So that's going to be our distance in our equation over here, 40 minus y. And then we just got to figure out what the weight of the slice is. So remember, we're given density. And density, in this case, is weight. It's a weight density. Weight per length. So if we solve this for weight, you're going to find that weight is density times length. And that's what we're going to use here for weight when we're finding the work for this slice. So we have delta times the length of the slice, and the length of our slice is just that infinitely thin length, which is dy in this case. Alright, so for the weight, we're using density times length to get delta dy, and then we still have the distance to be 40 minus y. So let's just clean this up a little bit. So our work is delta times 40 minus y dy. We traditionally like the dy to be written on the end. Alright, so this is exactly how much work is needed just for our little slice, and our slices are going to range from 0. So the first slice is going to be down here, and they're going to come all the way on up the chain until we get to a height of 40, to a y position of 40. So we want to add all those up. They're infinitely small, which means we use an integral. So the total work, total W, is the integral. We start at 0, we go all the way up to 40, and then we have the work for each slice, which is given as delta times 40 minus y dy. Let's remember what delta is. Delta is 2, and I can pull that out front because it's a constant. And then the integration from here is pretty straightforward. We just have 2 times 40y minus y squared over 2, and this all ranges from 0 to 40. When you evaluate this, you're going to find that you just get 40 squared over 2. The 2's are going to cancel. So we end up with 1600. All right. And this is work. This is total work. And our units are in the British system, so we end up having foot-pounds as our units. All right, and that would be the total work needed to pull up this chain. So let me zoom out here so we can get a big picture of what we did. Oops, excuse me. We recognize that calculus is needed, so we find the work for just a very small slice of the chain, and then we are going to integrate the work for that slice over the given region, and we find that we get 1600. All right, this is a very common and popular example when we're dealing with work with integration techniques, so it's good to master this one so that you can move to some more complicated ones. Hopefully this helps, and I'll see you guys next time.